So, welcome to all, and in this lecture, we'll describe the UV visible spectroscopy. And so, first question arises from this topic that what is the UV visible spectroscopy? Okay, so UV visible spectroscopy involve the study of interaction of UV visible radiation from molecules, or you can say with molecules. Okay, so it is the actually spectroscopy based on the interaction of ultraviolet visible radiations with the molecules. Okay, so this is the fundamental of UV visible spectroscopy, that how UV visual spectroscopy works. Okay, the second question arises, what is the result of interaction of UV visible light and the molecules? Okay, so first of all, what is the UV visual spectroscopy, and the second one is what is the result of interaction of UV visual light with the molecules? Okay, so the answer is the ultraviolet light and visible light have just the right energy to cause the electronic transition of electron from one field orbital to another of higher energy and field orbital. Okay, so the interaction of UV light, you can say UV visible radiation with molecules causes the electronic transition of electron, okay, within the molecules. And when electronic transition of electron occurs, then electron will be moved from field orbital to another high energy unfilled orbitals. Okay, so the next point, very important point, when a molecule absorbs light of appropriate wavelength and the electron is promoted to higher energy molecular orbital, the molecule is then in excited state. Okay, so first of all, what happened? The process, first process is interactions. See, from UV radiation with molecules, resulting electronic transition of electron occurs. Okay, and it is the appropriate wavelength of UV visible with interaction of appropriate visible light, appropriate wavelength of visible light with the molecules. Okay, and during interaction, what happened here? Electron is promoted to higher energy molecular orbital. The molecule is then in excited state. Okay. The next one is UV visual spectroscopy, possible transition organic molecules. So what happened? This is the energy. So if you see the molecular possible transition, then there will be possibility of non-bonding to non-bonding to pi star, or non-bonding to sigma star. And if you see the below of non-bonding electron, it is the pi and sigma. Okay, so there are 2 to 4 to 5 transition, 6 transition is possible. You can say sigma to sigma star, you can say sigma to pi star, and you can say pi to pi star, you can say non-bonding to sigma star or non-bonding to pi star. So it is the, first of all, you should know the energy, and then when electronic transition occurs, in between these, you can say non-bonding to pi star, non-bonding to sigma star, as well as pi to pi and sigma. Okay, so it is the sigma to sigma star occur in the only alkanes type of molecules. Alkane means only single bond molecules which have single bonds. Okay, and the second one is sigma to pi star. Sigma to pi star means it occurs in the carbonyls. Okay, sigma to pi non-bonding pi star occurs only in the carbonyls. Okay, unsaturated compounds transition occurs pi to pi star. Okay, non-bonding to sigma star occurring oxygen, nitrogen, sulfur, halogen containing molecules. Non-bonding to pi star occur in carbonyls. Okay, so these are the following transitions which occur in the organic molecules. Okay, UV, the next point is UV spectra of organic compounds are generally collected from 200 to 700 nm. Okay, so this is the range in which electronic transition occurred. Okay, so you can say sigma to sigma star occurs in the alkanes, and the range of wavelength is 150 nm. Okay, and it is higher in sigma to pi star. Okay, which occur in the carbonyls. I have previously discussed, it occur 170 nm. Pi to pi star occur in unsaturated compounds, and it is 180 nm. Non-bonding to sigma star occur in oxygen, nitrogen, sulfur, halogens means heterocyclic molecule atoms if present in the molecules, and the range is 190 nm. Non-bonding to pi star occur in carbonyls and the range is 300 nm. So unsaturated, you can see the pi to pi star occur compounds if conjugated, means conjugation system will be present in the molecules. Okay. So this is the figure representing the UV spectrometer measurement of observed radiations. So first of all, what happened here, when you can see this structure. So this is the sample cuvette. Okay, sample cuvette, and there are mirrors present in the spectrophotometer, and different granting as well as light source of UV light present in this. Two slit is present, slit 1 and slit 2. One filter is also present in this. Reference cuvette also used in this. Two detector, detector 1 and detector 2, as well as two lenses, lens 1 and lens 2 is present in the spectrophotometer. So it is the internal compartments of UV spectrophotometer. So next one is UV spectroscopy, and in this absorption law is applicable, and it is based on the Beer-Lambert's law. Okay, so as a given wavelength, absorption is proportional to the concentration of absorbing molecules. Okay, so absorption is proportional to the concentration of the absorbing molecules and the path length of light through the sample passes. Okay, so A is the absorbance of the sample, and it is the loctane I0 upon I. Okay, I0 intensity of radiations entering the molecules. I is the intensity of radiations emerging from the sample. L is the length of light. L is the length of light. L is the length of light path through the sample in centimeter, and C is the concentration of the sample in moles per liter, and sigma is the molar absorptivity and measured in liter mole inverse centimeter inverse. Okay, the molar absorptivity of a compound is the constant that is characteristic of the compound in a particular wavelength. Okay, so molar absorptivity, you can see the definition. It is the constant that is characteristic of the compound in a particular wavelength. Okay, so it is some basic representation of Beer-Lambert's symbols, which is the formula is A is equal to sigma CL. Okay, so you should be knowing what is the A, what is the sigma, what is the C, and what is the L. Okay, so next one is molar absorptivity may be very large for the strongly absorbing molecules, more than 10,000, and very small absorption is big, is equal to 10 to 100. No absorption gives means sigma is equal to 0. UV spectroscopy is the absorption law. So guanosine has a maximum absorbance of 270 nm. Okay, guanosine is the molecules in which nitrogen is present, and sigma is 275 8400 meter inverse centimeter is the unit of this, and the path length is 1 centimeter. Using a spectrometer, you find the that 8 to 75 0.7 is the concentration of guanosine. So simply you will put the all the digits in the A is to sigma CL. You can find the concentration and measured in mole per liter. Okay, and if you measure the sigma, then there is a formula minus log IT upon I0. Okay, so log IT is 0. You can see there is a, you can read this and you can 50% means 0.5, 1.0 it is the I0. Okay, so it's equal to A is equal to 8 sigma, so you can find the sigma value. Okay, so you can first of all you should be read this formula, and here absorption coefficient is asked. Okay, so you can see that this by applying this formula you can find the sigma. Okay, next one, presentation of spectra, how you can present this graph. Okay, so the ultraviolet visible spectra is generally regarded as a plot of observance versus wavelength. Okay, so it is the lambda max 195, and transition occur pi to pi star means in this double bond will be present, and this you can see lambda nm is 274, and non-bonding to pi star transition occurs in this molecule. So the choice of the solvents to be used delta spectroscopy is quite important. Usually solvent that do not contain conjugated system are most suitable. for this purpose. So absorbance and is the lambda NM. So lambda max is the wavelength when maximum absorption occurs. The next important point is chromophore, which is very important in UV visible spectroscopy. So chromophore is the part of a molecule that absorb UV or visible light. Okay. So chromophoric moiety, if molecules contain, then it will be UV active. Okay, and because it only absorb the UV or visible light. Okay. So it is the basic moiety which should be present in the molecules if you are going to analyze the UV spectra. Okay. So in alkanes, molecule contains single bonds, and the one molecules contain single bonds, and the only possible transition is sigma to sigma star. Okay. Observe ultraviolet energy at very short wavelength below 200 nm, shorter than the wavelength that are experimentally accessible 200 to 700 nm. Alcohol, ether, amines, and sulfur compound in saturated molecules that contain bearing non-bonding pair of electron, possible transition of non-bonding to sigma star. They are also high energy transitions. Alcohol amines observe in the range of 175 to 200 nm. Organic thiols and sulfides observe between 200 to 20 mm. Most of the absorption are below the cutoff points for the compound solvents, so they are not observed in the solution spectrum. And alkenes and alkynes, if you see, the possible transition is pi to pi star because it is the unsaturated. The transition are greater than high energy 170 nm, as well as but their positions are sensitive to the presence of substitution. So if substitution is present, then the value will be changed. Okay. Next one is carbonyl compounds. So unsaturated molecules that contain atoms such as oxygen, nitrogen may also undergo non-bonding to pi star transition and occur in 280 to 290 nm. Carbonyl compounds have pi to pi star transition to about 188 nm. So these are the some chromophoric and their particular values has been discussed in this. Okay. So in this lecture, we have described the what is the UV spectroscopy, basic of UV spectroscopy, the interaction, how what occur when interaction of UV visible light with molecules occur, and their molecular transitions, and as well as the Beer-Lambert's law and UV visible absorption law. So all the topics have been discussed carefully. And if you have any queries regarding this, please comment. And if you like this video, please like and subscribe this. Okay, so thanks for this.